Okay, so I said in lecture that we would have one more topic to cover here, and this will take about 10 or 15 minutes. So our first understanding of integral was when we were talking about we know how fast something is changing at every moment, exact rate function. We want to know how much of it we have at every moment. So that would be developing an exact accumulation function from exact rate. And how do we do that? So we looked at breaking it up into intervals, finding constant rates to mimic that rate function. And from those constant rates, we could get little bits of change. So the change from 1 to, say, 4.2 is the sum of the changes at these different constant rates. So here at the first constant rate, we get this much change. Second constant rate, we get this much change. At the third constant rate, we get this much change, etc. And we add up all those to get the accumulated amount at, say, 4.2. And so an alternate way to look at this is we can think of this little amount of change, R1 delta x, as the area of a rectangle. Why? Because the base is delta x. And the height of that shaded rectangle is R1. So since area of a rectangle equals base times height, that's fits the pattern of what we're doing here. The rate is the height, and delta x is the base, the width of the base. So we get R1 delta x. And we can think of then each of those little amounts of accumulation now instead as base times height, base times height, base times height. But that this is, the integration is related to area is only because of how we graph. We graph in rectangular coordinates where x and y are perpendicular to one another. And so this y value of the rate and the change in x form a rectangle, and these little bits of change then could be seen as areas of rectangles. But that's only because of how we graph. Okay. It's not a significant principle the way accumulation and rate of change is. Okay, so integration, building an accumulation function, is about using the rate to build accumulation. Because of the way we graph, coincidentally or incidentally, those little amounts of accumulation could also be represented geometrically as area. So what about if we take smaller intervals, then we get thinner rectangles. Thinner rectangles that do a better job matching the top of the curve. So if we let the widths of the rectangles get really small, then we see that adding up all those little bits of accumulation now is adding up all these the areas of these really thin rectangles, which now actually the tops almost perfectly match the top of the curve. So while this does work out with the geometry of things, that our amount of accumulation can also be seen as an area under the curve to the x-axis. It's a superficial way of understanding integrals. It's, like I said, it's incidental from the fact that we graph in rectangular coordinates. So let's summarize here. So now we have two versions of our understanding of integrals, and so let's summarize those. So before we saw f as a rate of change function, and if f is a rate of change function, then what does this represent? What does this represent? You should pause the video and test yourself. We've asked it many times, and it's crucially important. Then f represents the accumulation of a quantity with rate f with a reset at a. So the accumulation of a quantity starting at a up to x if the rate of change is f. That's review. That's what we spent the whole semester working on and discussing. it's the amount of accumulation. Now, if we look at, and that amount would be the y value here on the accumulation graph. Second version, now a new understanding of integrals, is that this f now could be any function. It doesn't have to be a rate function. It doesn't have to be, it can be rate, it could be accumulation, it could be amount, anything. Then what does this represent? It represents the accumulated area between f and the x-axis. That coming from summing up the areas of very, very thin rectangles, which is, this is the same calculation. We're summing up now. What is this? This is the height of the rectangles, and this is the width of the base of the rectangles. So it's the same process, but now it's a geometric view of it, summing up areas of very thin rectangles. So now we have two versions or two perspectives on integral. Accumulation and rate, and now area under the curve to the x-axis. So let's look at an example. So we're interested in this integral. Here's the function g, graphed here. This is the definition of the function, and here's the graph. Starting, and we're interested in from negative 0.5 to 4, this integral. So as accumulation and rate, we know that that would be the total change in the quantity whose rate is g as x changes from negative 0.5 to 4. And what would happen? What would happen to that if this g function is the rate? What would be happening in this part right here to the accumulation? Well, g is positive, so the accumulation would be increasing. Then we would get here, and for this part of the interval, g is negative. So then our accumulation would be decreasing. We'd be taking away from the total amount for this whole part. So we'd expect here, looking at the graph here, from negative 0.5 to about 0.1, the accumulation increases and then the accumulation decreases, and we would expect this amount of decrease to be greater than the amount of increase that we had here. So by now we're at a lower value than when we started. But then again, starting here at 2.8 to 4, the accumulation would increase again. And that would all be taken care of in here, because whenever the rate is positive, this thing would be, there would be a positive contribution to this. And whenever the rate is negative, there'd be a negative contribution to this. The accumulation would be going down for wherever that thing is negative. So that's all built into this. As g changes sign, so does the contribution to the accumulation change. And that's all built into that whole expression. So then, thinking of it as area, what does the integral represent as area? Well, from negative 0.5 to here, this would all be a positive, we know that it gives a positive contribution to this quantity. And so whenever the g function is above the x-axis, we get a positive contribution to this total amount. But here, because g is negative, what will happen? This area here, as x changes from here to here, will actually have a negative contribution to this integral right here. So it actually subtracts this area and then adds this area. So what we get is, we get net area by computing this integral. It would be, if this was a1 and this was a2 and this was a3, meaning positive, right? So all areas are greater than 0, because they are. Area is a positive quantity. Then this integral would compute a1 minus a2 plus a3. And that's consistent with how we know what we know about rate of change in accumulation. When x is in these values, between these values here, a negative rate will mean the accumulation is decreasing, going down, or a negative contribution to the total change. So as area, this area then would be subtracted from the sum of these two. So this is entirely consistent with how we thought of integral as accumulation. So how would we find, if this finds the net area, it finds a1 minus a2 plus a3, how could we set up an expression to actually find the total area? What would we have to do to compute a1 plus a2 plus a3? Well, that's what we want to do. We want to find the total area of a1 plus a2 plus a3. Well, what we need to do is we need to isolate. We need to isolate the three different regions. So we do that by, say, let's call this, whatever this intersection is x1, whatever this intersection is x2, and we've got to isolate things. We know we want to add a1, but to add a2, we know the integral will give us a negative value from here to here, but then positive from here to here, so we're going to have to split this up. To get the value of a1, we'll integrate from negative 0.5 to x1, and that will give us that area in red. But then to get this area, a2, we're going to have to integrate from x1 to x2 and then take the opposite of it, because we know that integral will be the opposite of this area. So if we want the actual area, we're going to have to take the opposite. And then to get the area of this region over here, it'll just be the straightforward integral x2 to 4 of g of x. Why? Because g of x is all positive there. So to get total area wherever you have a function that's dipping below the x-axis, you need to isolate the different pieces, and whatever pieces are below, whatever regions are below the x-axis, we need to take the opposite of that integral as x1 goes from left to right. So to get the total area then, we need to add this integral, but then take the opposite of this integral, or subtract it, and then add this integral, and that expression then will calculate the total area a1 plus a2 plus a3. Whereas the single integral from negative 0.5 to 4 will compute the net area. It will take this area minus this one. It will equal a1 minus a2 plus a3.